will create the base setup for the procedural terrain generation, which will work using a chunk system in order to efficiently generate infinite terrain. We'll also make a very simple setup to procedurally blend between the different character animations. So let's get to it. The core of the idea is to work with chunks of fixed size and have them move under the character's feet, so that once a chunk is too far out of sight, we just move them back in front of the character, and so on, to have a seemingly infinite terrain while not taking too much space in the memory and not having to generate the full terrain while only displaying a small portion of it. Let's hide everything, add a new object, and rename it O1 Terrain. We will work with several simulation node setups, so the order in which we make them is important. That's why I like to put number in front of my object. We can also right away move this object into a collection named Simulation. In the Geometry Nodes tab, you can add a new Geometry Node setup and rename it Terrain Generation. Add a Grid Object node and plug the mesh into the geometry output. You can straight away put the size of the grid as new parameter and do the same for the vertices. Shift right click to add a reroute node, hit N to open the sidebar, and under group, you can rename the new inputs. I want to call it chunk size, and the vertices will be collision mesh resolution. Now let's add a new parameter for the number of chunks we want. Set the default value to, for example, 3, minimum to 1. As ballpark values to start working with everything, I like a chunk size of around 2, collision mesh resolution around 16, and let's start with 3 chunks. To create the chunks, I will just instance my new grid object onto a mesh line, plug the count into chunk number, and add an instance on points node. Plug the mesh line into points, and mesh into instance. For the parameters of the chunk line, set the mode to endpoints, and compute chunks number minus 1 with a subtract node, multiply it by the chunk size, plug that into a combined XYZ node, under the Y input, add a vector mass scale node, set to 0.5, which you can plug into the start location, Ctrl-Shift-D to duplicate this one, set it to minus 0.5, and set that to the end location. Add a reroute node to clean everything up a bit, and I am even duplicating the group input to replug everything in a cleaner fashion. So this is the basis of our chunk setup for the collision plane. Now let's move on to a simulation setup so that we can offset the position and have this work as a treadmill under the character's feet. Realize these instances, plug this into a simulation zone. In the simulation zone, add a set position node. If you start with a small offset value on the Y position and press play, our ground will be moving in one direction, but the chunks are really quickly going out of the sight. The easiest way to go around this is, instead of working with the global position of each point of our mesh, we just want to know the position of a point inside its own chunk and the center position of each chunk. It's quite easy to get those values. Between the realize instance node and the simulation node, add a store named attribute set to vector and call this local position. And add another one right after the mesh line, set to float, and call it chunk Y offset. Just plug in the position through a separate XYZ node and plug the Y value into the store attribute node. For our local position, we just need to get the position of each point and subtract the position of the center of each chunk. So get a named attribute, the chunk Y offset, plug that into a combined XYZ into the Y input, and this into the subtract node. If we visualize this attribute, we just have the position of each point inside the chunk. Now, because the chunk Y offset will vary along the simulation, we also want to store its original value. So duplicate the store named attribute node and rename it chunk Y base. You can plug in the same value. You can select all that, hit Ctrl+J, and label this zone initialize chunks. Also do the same for this and rename that store position attributes. Now inside the simulation zone, Right before the set position node, we want to increment the chunk Y offset. So add the store named attribute node, set it to chunk Y offset, and add the named attribute node set to the same attribute. So at each iteration, we just want to add a small value to the chunk Y offset. And we can set the position by getting the chunk Y offset, combining it into a Y input of a combined XYZ, and just add this to the local position attribute. Plug that into the position input of the set position node, and if we run the simulation, for now it's looking the same. But by doing it this way, we can check the chunk Y offset attribute right before combining it with everything to make sure that the value is always within something which is into our field of view. So quite simply, a math wrap node right here, plug that into the Y input. Now we just need to set the wrap values properly so that the distance between all chunks are always the same. Add a group input node. The maximum bound will just be the chunk size multiplied by the chunk number divided by 2. And the mean value will be the same, but with a minus sign. So to do this cleanly, let's just Ctrl-Shift-D duplicate everything and divide it by -2. Now if we play the animation, everything is moving, but each chunk is continuously being put back at the end of the animation. Let's put all this into a frame and call that compute chunks position. Let's just keep in mind that for now, the only thing controlling the speed is the value we add at each frame to the chunk Y offset. Now let's get some deformation to our terrain. That way, everything will come together. So first, let's do something quite naive. Add a noise texture and plug the FAC into a combined XYZ to the Z input and plug that into the offset. So this is the same as having the vector plugged in with the position node. By reducing the scale, it looks better, but it doesn't really make sense because the deformation should be moving along with the ground. So what we need to do is compute another kind of position to plug in into the noise texture, and the position that we will compute is in fact a kind of simulated position of the real point at which each point is supposed to be if the ground wasn't moving. To compute that, we first need to know the difference of position between the chunk Y offset attribute and its wrapped value. So add a subtract node and plug in first the chunk Y offset position and then the result of the wrap operation. So this will give us the offset between the real Y position and its simulated one. Then we need to offset that by the original position of each chunk. So add another math subtract operation, and for the attribute, put the chunk Y base. You can put the result of that into the Y input of a combined XYZ node. And if you plug that into the input of the noise texture, of course at the moment it's just one value per chunk, but already it makes a bit more sense. Now we just need to get a different value for each point of the chunks. You could think that the solution is just to add this to the local position as we did before, but if you do that it's actually flipped because of all the operation we did, so we just need to set that to subtract, and now it's all behaving properly. So we have the base of an infinitely moving terrain, which always regenerates new position. Of course, the only inconsistency now is that it's not looping, but that will be a problem for later. Now let's just complete that a bit. For the noise texture, because it outputs a value between 0 and 1, we need to offset it by 0.5 before combining it with XYZ, so that it's centered around 0. And we can also multiply by some value, so we can control the height of the terrain. Now for some more flexibility, I like to put my noise to 4D, so we have a new W parameter, and we can group all those 3 nodes and plug everything as new parameters, with the final one being named height. This node group I like to call noise centered. You can also do the same with the color output by subtracting 0.5 as a vector and multiplying it as a scale. To control all that, we can also put all those noise parameters as group inputs, so we have one single place to control everything, which will be handy later when we will duplicate this noise-centered node. We can select all that, press Ctrl-J, and label this frame compute terrain height. Let's just clean up everything a bit. Now because of the final treadmill effect we want to get, so I want to add a new parameter to kind of compress the deformation along the Z-axis. So add a new input parameter and call it X compression, I'm just moving it higher a bit. Plug this into the X input of a combined XYZ node with the other values set to 1, and plug that into the second input of a vector math multiply node, which we are going to put in between the subtract node and our node group from before. Now, by playing around with the X compression, we kind of have the terrain deformation centered along a single axis, which is the axis of the movement. Now, by playing around with the parameters, we have a nice treadmill effect. Now let's take some time to fix another effect. If we want the camera to stay fixed, we don't want the terrain to move too far out of sight in the Z direction. So what we want is to have the terrain always cross the center of our world. To do that, we need to offset the Z position, which we can do after the simulation output. It will be quite easy to compute this. Just add a raycast node. For the source position, you can use a combined XYZ node and put the Z input into the height of our group input with the ray direction facing down, and for the ray length, you can put the height multiplied by 2. For the target geometry, right now you can just put the output of the simulation zone, and to apply this offset, you can add a transform geometry node and plug the hit position into the translation. So just add a vector math scale node, set to -1, and now if you press play, everything will be centered around the origin, which is a pretty nice effect. Let's select all this, Ctrl J, and label this frame Fix Z Offset. Now let's see how it looks with our character. Unhide our main character, and as of now, it's only referencing the terrain collection we generated before. So now instead of having a displaced texture map the height of the terrain, you can add a shrink wrap modifier and target our terrain. Just set the wrap method to project, and just click on negative and positive, and also we can take the armature master and lower it just a bit. So now, besides the speed of the animation and the choice of each animation which we need to fix later, everything is already looking really nice. So now just something along the shading line. For the terrain collision realize, you can check disable any renders, and under object properties, under viewport display, you can display as wire. Also, under visibility, you can uncheck everything, just to make sure that it doesn't show in the render. Now here we have some kind of glitch because of the raycast node, but the reason is quite simple. It's because at the moment we are just doing a raycast vertically to find a collision with the terrain we just generated, but remember, as the terrain is composed of chunks, there are still really small gaps in between each chunks. So to fix that, before the raycast, we can just add a merge by distance node, and that should fix that. Now at this point, the simulation zone isn't really useful, because the speed is constant. You could just do that with standard geometry nodes. But now let's make it useful. We want to change the speed depending on the slope which is directly under the character. So if the reference is upward and the angle of the normal is in this direction, so the angle is negative, we want the speed to be slower because the character is running uphill. And if it's in the other direction, meaning the character is running downhill, we want the speed to be higher. And once the speed will be correctly implemented, we'll also use that to blend between the different character animation. So we'll have the walking animation when it's uphill and the running when it's going downhill. So to get the normal, let's use the same settings as before. Let's duplicate this, Alt-P to remove them from the frame and plug the geometry inside this. Now with the hit normal, we want to get the angle. Do that, use the align to Euler node and plug the normal into the vector, and for the angle, we want to align the V vector. So then, if we separate XYZ, the X component will be the angle of the slope. This angle will now be used to blend between 5 different speed values. To do that, we need to define 4 angles which will act as boundary of the 5 different states. Take the angle, add a greater than node. This will be the first angle. If we duplicate this with Ctrl-Shift-D a bunch of times, we will have the comparison with 4 boundaries. Now I want this to output a value between 0 and 4 for 5 different states. The easiest way to do this is just to add all of those values. And we can put all of this into a notebook, so it's a bit cleaner. I'm going to put all of those boundaries of the B value right here as boundaries, and I'm just changing the name of the inputs. The first one will be angle. I want the subtype to be an angle, the same for the other. The first will be the limit between the state 0 and 1. Then we have the limit between 1 and 2, limit 2, 3, and limit 3, 4, with all the subtypes set to angle. And for the output, we name this the state, which in this case is just an integer value. This is going to be angle to state. And from my tests, I found that the best limit between the work heavy and work normal is around minus 30 degrees. Then between work normal and run normal, minus 15 degrees. Between run normal and run fast, 0 degrees. And run fast to run fastest, 10 degrees. And now from this state, I want to blend between the 5 different values that we have for the speeds. So first I can plug this into the factor input of a mix, and I can change this 4 times. So we have our 5 inputs. Again, I can group everything and plug everything here, and then rename everything accordingly. The factor is, in our case, the state, which will be a float value this time, as we will convert it later. Then we have value 0, and so on. And the output is just the result. Mix everything correctly. We actually need to plug the state -1 each time for the next stage. And this is the state value blend. The unit of all those values for the speed is just meters per second, and with the animations at 30 FPS, I measured all of those values from the mix samo data and putting them into my notebook. With this speed, I can multiply that with the delta time of the simulation zone, and the result now is the distance, which I can just add to the chunk way offset of each iteration. Now if I go to the beginning and play the animation, we have the speed of our treadmill, which is varying depending on the slope of everything. Of course, at the moment, there is absolutely no smoothing, so if the terrain is very rough, the speed will move just over the place. So that's the next thing that we'll fix. But first, let's tidy up everything a bit. Now that we have the first setup of our different states, we can pass all this information to our character, so it can also use this to blend between the 5 different animations. To do that, we actually need to output the states outside of the simulation zone, and this time the value will also be a float. And right outside, I can use a store attribute node, plug that in, and name this state. Then on our character, I can add a new geometry node setup right before our armature deform modifiers, and I'm going to add this and call it animation blend. So just dragging our terrain. It doesn't really matter, but you can set it as relative. And now I just want to sample the index, and for the value I'm just going to take a named attribute, and here I'm fetching the state. Now if I display this, we should have the color depending on the slope of everything. So it's working properly. We need the value of the vertex group. We just need some store named attributes node set to each of the new vertex group we just put. So work heavy, work normal, and so on. Again, the order is important. And for the value, we can always set the first one to 1, because we always want at least one animation, and the other we just override this one. Then we can plug the sample state into the second store attribute, so that the work normal animation will be activated when the state is varying between 0 and 1. Then for the second one, we want it to be activated when the state is varying from 1 to 2. So to that, we can just subtract 1 and clamp the value to make sure the values are not outside of this range, making the animation too strong. The third one, we want it to be effective when the value is from 2 to 3, so we can remove 2. And finally, we can remove 3 for the last animation. Also, at the moment, the transitions are really sharp, but it's just because all the animations aren't synchronized. Because of their different lengths, the foot doesn't always make contact at the same point, so there is a lot of sliding. But we'll also solve this later. We are going to fix the slope detection in a number of different ways. The first one is to use a lower resolution plane for the slope than for the collision. So let's duplicate this setup, add a new input for the slope mesh resolution, which I am right away going to set to around 4, and I'm going to plug this here. Now I'm going to join those two setups, and I will add attributes to differentiate them when I want. Set to Boolean, so the first one collision and the second one slope. So I am adding a separate geometry node with a name attribute where I'm going to fetch the slope. Then in our terrain collision realized, I can remove the shrink wrap and subdivision, add a new geometry node setup. I am going to call it fetch attribute. So I can add an object info node, set to relative, the object as input, add a separate geometry node, named attribute, set to Boolean, and the name I can set as input too. And like this, if I select my terrain, and for the geometry I want the collision, now I get all the parts of the mesh that I want. Back to the terrain, I also want the slope for this one. And I can even push this further with the blur attribute node, set to vector. I can blur the position, which will effectively smooth the mesh even further. So after the merge by distance, I can add set position node and just plug our blur value into the position input. Now for the iteration, I can put a bit of a higher number and set the weight as an input. Sloped mesh, smoothing. Now if I take this, even if I increase the detail and roughness, the change in speed should be way more stable. But at the moment, the change in speed is quite abrupt, so to smooth that, we are going to implement a kind of blend between the different states, so we'll be able to mix the new state value with the previous value, which will ease everything. The node group we are going to create will basically implement a kind of attack and release to the values. So here, because we already set the state value as a simulation input and output, we'll be able to blend the new state value computed each time with this value, which is the previous state. And basically, how it works is we are going to add to the previous state the difference between the new state and the previous state multiplied by some factor. And this right here is a really simple version of an attack and release. Depending on this value, the new value will have more or less effect on the previous value. For example, with a really small value, if I plug this into the new state and into the state of the next step, everything is already going to be way smoother, even though we still have some issues between the different animations because they are not synchronized yet. We can already set that as a new group, select everything, Ctrl G, and here the first value is the target, and the second is just our previous value. We can set the value in the multiply as an attack value, and we can also add more control by Ctrl-Shift deduplicating this one, adding this as a new value, which will be the release. And to switch between those two values, we just need to test the value is greater than the target and switch between those two. Set as float. If the value is greater than the target, then we are going to use the release. And if the value is not greater than the target, we are going to use the attack and plug that into the add value. So this is an attack release. Because the angle still directly controls the states, we can also add an attack release right after we computed the angle, so that even with all the smoothing on the slope mesh, it will be smoothed by the attack and release block. So this will be the target, and to use it, we need to add a new value to our simulation node, which is going to be the angle. We can set the attribute, and we can output that to the simulation too. Now I will probably tweak those attack and release values for those two blocks all along the process, but you can play around with those values to see what you like best. And finally, for this step of the base setup of everything, I'm going to duplicate the terrain collision realized and calling it terrain slope realized. Here I just want to get the slope, and with a bit of the subdivision surface so it's really smooth, I can add a shrink wrap constraint to the armature master so it will always stick on the surface, even if you have some kind of vertical movement. With the mode being set to project on the vertical axis, project opposite, and snap mode being set to on surface with a small distance offset, so it's always a bit under the mesh. And the output mesh isn't merged, so we are going to fix this right before the fix the offset and moving everything a bit on the side. You can remove the merge by distance here. And here you can add 2 merge by distance nodes with some named attributes, one for the slope and the other for the collision. And that's it for this part. Hope you learned something here. The next part will be focused on making a very simple script to make sure all the animations are synchronized and to procedurally change their speed depending on the geometry node data. Feel free to reach out to me if you have any question. Thank you for watching and see you next time.